Okay, let's go.
So we are going to continue with 1.2. Trying a slightly different view on the camera today, so tell me if you like it better or worse. But we spoke about linear equations and modeling with linear equations, minor cells with equations. And we did one example, the lemonade stand example, part 1. So now we're going on to something called break-even analysis, which you saw on the bonus problem quiz. Break-even basically means the amount of money you're making is equal to the cost. So you say you've broken even. Very definitely define that. Okay. Let me define the two terms first. That is revenue. Loosely speaking, this is the amount money made in transactions. Ignoring any costs incurred. So we call that the revenue. It's literally the amount of money you bring in from your business activity, okay? And you ignore all the costs associated with you being there. So in the lemonade stand example, if I'm talking about my revenue, I'm talking about how much money did I make from selling cups of lemonade.
So
I'm not going to say, oh, it cost me $1.50 to make lemonade, so technically I made this much. Doesn't matter. It's how much money we bring in. That's called revenue.
So whatever we sold back plus whatever the overhead is for the function revenue?
No, revenue is literally how much money you bring in, there's nothing else. Overhead, not considered. Cost, not considered. Nothing is considered except the money you bring in from the activity. So it's literally how much I would have made by selling a certain amount of lemonades, ignoring overhead, ignoring costs, ignoring everything except the money I've gotten from customers. Okay? So this is called revenue. Now, there is another term that's going to be important, in which you would consider overhead and all that stuff. This is called profit. So let's say again, I'm selling lemonade or whatever, and on this particular day, the ingredients that I have to make the lemonade in total cost me $100. That day I sold $500 worth of lemonade, working hard. Then you would say that the revenue is $500 because that's how much I made from selling lemonade. The profit is actually $400, right? Because now I'm talking about the money I've made minus what it cost me to make that money. I'm just talking about how much I'm ahead from that activity. So the profit factors in the cost and overhead and all that stuff. But when you're talking about revenue, you don't care about any of that. You just care about what money you're getting from your customers. So those are two very important things. And you might have, did I define something else? No, depreciation is going to be this. So we have the equations. So given that that is revenue, how do you think revenue would be computed? So let Rx equals revenue from selling X items. let's say P of X equals profit. So what would you say R of X is equal to? How would you compute revenue? Yeah?
The price you're selling it for times the number of items sold.
Right. Price per item times the number of items sold. This is just a simple multiplication. If I'm charging $2 for a product and I sell 10 such products, I would have made $20 revenue. So that's going to be it. And we'll talk about the price later as well when we get to economic functions. There's going to be factors that go into us choosing the right price that we want to do. But once we have picked a price, multiply that by the number of items we sell, that will be the revenue. So that is the first equation. The second equation is the profit equation. How do you think that is computed?
Minus cost.
Revenue minus cost. Tell me how much money I have doing this activity. Now subtract how much money it costs me to actually perform that activity, and this is how much I'm ahead. Right? This is called profit. Right? Now, in general, there's no general equation for cost. Right? Cost is very specific. It depends on the individual, right? It depends on your location. You know, if you're renting a facility or you're owning a facility or you're just on foot or how many people you're paying, right? The situation will vary. What your costs are, what your overheads are, it will vary. There's no general definition for cost. It's very specific to the business model. But revenue is in general computed this way, and profit is in general computed that way. You can take these as fixed equations. So pretty much any time where cost will be a factor, it will be given to you in the problem. So I believe in the extra credit, did I actually give you a cost here? Yes. Okay. So cost will have to be given to you. Okay. So the function c of x is given. Given in the sense that it's specific to the situation. So it's something that you compute once you're in the situation. You start to keep track of everything and you can figure out, here's the cost associated with this activity over this period of time. Once you can find cost, and you can find your revenue, you can find your profit, this is pretty much how much better or worse you are at the end of some activity. Okay? Did you make money or did you lose money? And that's important. Profit can be positive or negative. Hopefully you're not giving items away, so revenue should always be positive, but profit can be positive or negative. And the interpretation is positive means you made money. So you're ahead, right? Negative would mean you lose money. Lose. So that's bad. If I sold $100 worth of items, but it cost me $500 to even do that, I have lost $400. I'm worse than I was before, and that would show itself in a negative profit. So these are some important definitions. Now we can talk about break-even analysis. We'll talk about this, how this all fits together, and there's a section we're going to do on economic functions where we'll see how everything kind of fits together. So now, the break-even point. Break-even point is the point where the revenue is equal to the cost. That is, profit is 0. Right? So a lot of times you incur costs before you even start doing anything, right? You had to rent a facility before you started getting customers and before you start. So you kind of start out in the hole. And as you sell products, you get more money bringing in, so you're recouping your cost. Eventually you'll hit a point where your profit is going to be 0, which means the amount of money you've made is now equal to the cost that you've incurred. And the goal is, of course, to go beyond that point, so you start making money. Okay. So that's the break-even point. It's not always that way, it goes linearly. Sometimes you pass it, but then you might come back and hit the break-even point. It's a very important point to know. That's the point you hit when you're making no money, when your costs and your revenue are the same. You need to know when that point happens. So you need to know if you need to change something, do more of something, do less of something, etc. Let's continue the example then. So we're going to do part 2 of the example. Okay. So remember the first example is the lemonade stand. Okay. Just to remind you of the situation, recall Jhevon. Okay, so we have weekly fixed payments costing $100. Cost $1.50 to make a cup of lemonade. So I bought a lemonade stand and I'm making payments to pay back what I bought it for. Right? So I got it on a loan. I financed the lemonade stand. So now we're doing part 2. What is the revenue function? Bought a lemonade stand, sell lemonade. I borrowed the money to buy the stand, so I'm financing it. It costs me $100 per week. And it also costs me, ingredients and everything factored in, $1.50 to make a cup of lemonade on average. So right, so that's me paying attention to my grocery bill and paying attention to the cups and the ice that I'm buying and etc. And on average I realize, you know, pretty much for every cup of lemonade I sell, it's gonna cost me $1.50. What's the revenue function? Yeah.
I have a question. How much are you selling the lemonade for? Is that $1.50 or?
Yes, I forgot to tell you that. Selling for $3 per cup. It's good. It means you're paying attention to the definition. You realize that what I told you wasn't enough to actually do.
So it would be 3x.
3x, that's it. And again, where x equals the number of cups of lemonade. So I bought the lemonade stand, I'm making fixed payments of $100. Cost me $1.50 per cup to make a cup of lemonade. I want to make a slight profit, so I'm gonna I'm gonna double that price, selling it for $3. Revenue function therefore will actually be 3x. So here, ignoring cost, how much is made from selling 25 cups of lemonade? So cost is not a factor here. So this is just going to be the revenue function evaluated at 25. It's just going to be 3 times 25. It's going to be $75. You'd also notice that at this point I am still in the hole because it cost me $100 just to be there. Plus it's costing me $1.50 for every cup of lemonade I'm making. And at the point where I've sold 25 cups, I'm only pulling in $75. Okay, so let's continue this. What's the profit function?
Revenue minus the cost.
Profit is revenue minus cost. What would that look like here?
So that'll be 75 minus 150x.
45.
What is R of X? What's your revenue function?
75.
We want the equation of 3x.
This 75 is the revenue made from selling 25 cups specifically. Here I want the general revenue function.
Also 3x.
So that's going to be 3x minus, what's the cost here?
1.5x.
Minus 100.
So that's my profit. There is a flat fee that I'm paying of the 100. I'm also losing $1.50 for every cup of lemonade I make. If I'm making X cups of lemonade, I'm losing 1.5x. And I'm bringing in 3x. So that's my revenue, and these are my costs. So this is cost per cup, and this is cost for the stand. So this is my cost, and this is revenue. So in other words, I can simplify this a little bit. 1.5x minus 100. This is going to be my profit function. In this very simple example. Okay, so what is the profit sold if what is the profit at this point? What is the profit after 25 cups sold? How'd you get that?
Yeah, so you can combine
So
3x
1.5.
Right, so you're gonna go to the profit function, and you're going to plug in 25. So it's 1.5 times 25 minus 100, and that gave you what? Negative 62.5. So what does that mean? How would you interpret that number?
It's a loss.
It's a loss, right? You're losing money. This is a loss of 62.50, right? So if I only sell 25 cups of lemonade in this scenario, I will actually be $62.50 in the hole. I would have spent $62.50 more money than I actually brought in. So now here's the question. How many cups would I have to sell to break even? I think someone shifted the camera. Hopefully that hasn't been there long. cups to break even?
Could you set the function or whatever to 0? Would that work?
Which function?
The 1.5x function.
Okay, break even, again, we know this means profit equals 0, or you can think of it as revenue equals cost, but either way, what you can do is you can end up setting this equal 0, 1.5x minus 100 equals 0. This means what does that mean?
The solve
Yeah, how would you solve it?
add 100 close and divide by 1.5.
What is that?
66.66, so 67 cups.
66.6. Okay, so this means, right, so the break-even point, I mean, it's not going to be exact here, of course, but we need break-even point. It's around 67 cups. Right, at that point, I'm just starting to break even. Sure, I'll make a few cents over what I've spent, but at that point is going to be where my profit hits 0. Okay? In other words, what a break-even point can tell us, it tells us what we need to aim for. Right? So in our current situation, when we factored in costs, we know how much it's costing us, what our fixed costs, our overheads are, we know how much it's costing us to produce each product, and we know how much we're making by pulling in a product. The break-even point is going to be the target. It's going to be like, I know whenever I go out there every week to try to sell lemonade, I need to sell at least that much, or I'm losing money. If I'm not selling 67 cups, it's a bad day. Okay. So that's the use of the break-even point. It tells you where you have to hit to actually start making money. Right? Before 67 cups, I'm not making any money. So you need to make sure I pass that point. That's a lot of lemonade to sell, so this is probably not a great business model, or I need to cut costs somewhere. Because that is not, I don't think it will be fun to sell 67 cups. Okay, here's another thing that's very important here. These kinds of scenarios, it's called depreciation. Anyone knows what depreciation is?
Value loss is something that gets older.
This is a loss of value over time. That is also something that's very difficult to compute. It depends on the situation. Okay, so difficult to compute in general. And it can depend on a lot of things, down to the reputation of the product, right? So something might actually do the reverse of depreciation if it has a high enough reputation. It might actually gain value over time. But in general, things will lose value over time as they become more run down and wear and tear sets in. And how fast this happens will change. However, the class will often assume linear depreciation. So we're in the section on applications of linear functions. And this is depreciation that happens at a constant rate. So every year it loses a specific amount of value, which is the same amount of value every year. And this might be used even when it's not exactly what should be used, but it's a good approximation of what should be used. Depreciation. linear, this is depreciation by at a constant rate. That's what they have being constant. This would also mean, i.e., if we graphed the depreciation curve, it would be a straight line. It's called linear depreciation. So we're going to depreciate the lemonade stand. That's where we basically want to go. So what we can do, we also have an equation here if I want to make something more specific. So we have a depreciation equation. This computes the value, the money fair value remaining in a depreciating asset. And it is given by d of t. Usually our variable is time. We're talking about depreciation over time, over a few months or years or whatever. And in general, this is computed via figuring out what it's worth now, initial value. And obviously that is going to be reduced over time by some value. And this is going to be the depreciation rate. And of course I'm talking about linear depreciation. This is straight line. Right? So that's going to be the value. It reduces by per unit time. And then you're going to actually multiply that by how many units of time that have passed. Since your initial value was calculated. Now sometimes they write this as shorthand. V for initial value minus RT. This is called the depreciation equation. It tells you the value remaining after T years. T units of time, usually years. So this is called depreciation. Depreciation is a loss of value. Most things lose value over time. And difficult to compute in general, but sometimes you assume it's going to be a linear function. And so this will be how we would compute it. Tell me what it's worth now. Tell me how much money you expect it to lose over time. And then tell me how much time passed. And that will tell me how much it's worth at that point. Depreciation is very important. You'd often want to know how much your assets, your current assets are worth. For various reasons, including guys have a business or anything, sometimes you can even get tax rates based on depreciation. You can say that, oh, my assets have decreased in value, this is like a loss to my business. So you come with some equation that hopefully checks out with the IRS. Anyway, let's move on to part 3 of the lemonade stand saga. So, selling lemonade isn't my long-term plan. I expect to sell lemonade for 5 years, then retire. Now, I'm telling you the original price of the stand, bought stand, for $1,000. So I buy it for $1,000, which I got on finance. Remember, I'm paying $100 a week. I expect at the time I retire, I expect to be a resale value of the stand of $600. Okay? So I bought it for $1,000, and I'm expecting at the end of 5 years when I retire, I can probably sell this and get $600. Okay? For whatever reason that I assume that. So now we're going to, the problem is going to tell you assuming linear depreciation. And again, you would have to be told this because, as I said, depreciation is hard to calculate. You need to be told this. Depreciation is not linear in general. So you have to be told, you're assuming that it's depreciating linearly. So now the question is, how much did the stand depreciate per year? Secondly, let me just write this, let's just write this down. What is the depreciation function? C. How much is the stand worth? Three years after purchase. Where does this thing keep shifting? Because you didn't touch it, right?
No.
I kind of just kicked.
Huh?
I kind of just kicked with it.
Okay, don't kick it. Why are you kicking it?
Well, I wasn't.
Stop kicking. If you can't control your leg, go sit somewhere else.
Move towards the right a little bit.
I'm gonna put you on camera. Like, that's the kid that keeps kicking it. Every time you see the camera goes away, it's that guy's fault. Why does the camera keep shifting? It's restless leg syndrome. Okay. What is the yearly depreciation of the stand?
What is he paying?
Huh?
80.
$80 every year? How did you get that?
400 divided by 5.
Okay, so you can say difference in value. Would be 400, and this is happening over 5 years. So depreciation rate is just 400 over 5 years. So this gives you $80 per year. Now, one thing I want you to appreciate that you just found, geometrically, do you realize what you just found?
Yeah, the rate per year.
Yeah, that's in words, geometrically, as a mathematical idea.
The slope.
You just found the slope of the line, okay? You basically did rise over run, right? So that's the y2 minus y1 over x2 minus x1. Basically, if we're plotting this thing over time, if we're plotting the, say, the value over time, we know it starts at 1,000. And then after 5 years, it ends up being 600. So it starts here and it goes to here. And we're assuming it's a straight line. So this difference here is going to be 400. That's going to be your rise. But of course it's a minus sign because it's decreasing. And this here, that's 5, that's your run. So basically you did rise over run. And if you didn't see that that's how you should have calculated it, you should draw a picture. So that's telling you it's linear, it helps you in that way. Sometimes if you can't think of the calculations to use, just draw a picture and then you can actually figure it out. So the slope is the depreciation per year. And that's kind of talking about rate. Slope gives depreciation rate. So you actually found the slope of that line. Now technically it's going to be, the slope of the line is negative, but it's a loss in value, so it's understood that it should be negative. And so now, what is d of t? What is that function? Now we drew the picture, so finding the function should be easier. What would that be equal to?
80 times 5.
80 parentheses 5.
So d of t is that guy, right? Which is a straight line. How do you find the equation of a straight line?
Is it 80t?
ADT.
Where time is year, so every year depreciation.
1,000 minus 5R.
So if you were to draw y equals 80x, what would that look like? What would that look like?
Negative 80x plus 1,000. Would that be the?
Yeah, so remember it's mx plus b, well mt plus b is kind of what you're thinking about. M is the slope. Here we know it's negative 80. So that's how much it's losing per year, plus the y-intercept, which is 1,000. Or you can think of it as 1,000 minus 80t, based on the formula that I wrote on the board previously. But that's the equation of that line. Okay, so that's your d of t. And this formula applies for your t going between 0 and 5 years. That's going to be the formula. It's a linear equation, it's just the equation of that line. So it's the slope times the variable plus the y-intercept. Don't forget how to find equation of a line just because we're introducing new phrases here. Okay, how much would it be worth 3 years after purchase?
760.
So this is just asking for d of 3. So it's just going to be 1,000 minus 80 times 3. Which is gonna be what? 760. So assuming I'm right that it is depreciation linearly, it will be worth 600 after 5 years. It should be worth around 760 after 3 years. Let's get some more interesting points here. So I call this the bonus round of the handout. A. Suppose we want a profit of $5,000 in a 2-week year. Say I'm selling year round. How many cups do I need to sell? You say it was a good idea to actually purchase this stand, Steve? Was this whole lemonade business a good idea? I'm gonna change the scenario a little bit. Well, how would you do A? Huh? So know that profit is equal to what? Oh, we computed that earlier. That what it was.
And then substitute the
Well, we actually found this earlier. So what was it?
$1.50x minus 100.
It was what?
$1.50x minus 100.
0.5x minus 100. And so how would I figure out how many cups to make a profit of 5,000?
plug in the 5,000.
I give you 3,400. What about per week? That was the original present answer. 5,052 week year, want to make 5,000 per week. So this was cups in a year. This means we need 3,400 over 52 cups per week. What is that?
65.
65 cups per week.
Wait, where did the 52 come from?
Oh, because I'm assuming a year has 52 weeks, so I do per week. So this profit was, the 5,000 is over a year. So to make that, I need this many cups, but that's talking about in a year. So I just divide by 52 weeks. Would you say it was a good idea?
I don't think so. It's less than 10 cups a day.
Huh?
It's less than 10 cups a day you have to sell. Work 7 days a week, so not that much.
He's an optimist. Yeah, it's not that bad. But this is 5,001.5 x plus. Oh, well, something is off here because that's not the answer.
3,400 divided by
Bec-
52.
Because what? Because what?
3,400 divided by 52 to 850 by 13, not a rounding.
Yeah, but it's worse than that because we also saw that we needed at least 67 cups to break even. So there's no way we can make a profit by selling 65. So something is off. What do you think is off?
You didn't add the cost.
What's the cost?
Another 150.
Huh?
100 per week.
It's 100 per week, right?
Mm.
And we're looking over a
So
year.
make that 52.
So this should be actually multiplied by 52. So that's going to give us what? 5,200, right? And so if I bring that over, what do I get? So that's 10,200. 10,200 over 1.5.
6,800.
That's 6,800
Yeah.
in a year, which means per week it has to be 6,800 over 552, which is what per week? 131. Okay, that makes more sense. Right, 'cause we need 67 to break even. There's no way 65 is going to get us a profit. So a little more than 10 cups a day now. And it's also worth noting because the situation is a little bit more complicated here, because then you'd have to worry about how many payments should you be making actually? So all that starts to come into play, because really, remember we assumed we bought the stand for $1,000 here. I'm gonna pay back 5,200. What the hell kind of a loan is that? Yeah.
Let's take out 100 times 52 and put 1,000.
And put a what?
1,000, you're paying no interest on it.
Yeah, if you're paying no interest, you could replace that with 1,000 instead of 5,200. That would break even, right? So there's the scenario. So these are just some things I want you guys to start thinking about, or confusion might happen. So if no interest on stand, max cost is 1,000. And then we can start throwing interest here. But I don't think you guys do a lot of interest stuff, actually. Then you would use P equals 1.5x minus 1,000. So this is you paying off the stand. We can assume that making 100 payments of 100 a week, you would actually pay it off in more than in less than a year. So you just set the price there, and then this is what it costs you to make a cup of lemonade. So this is cost of the stand. And money made per lemonade. $131 cups a week, not that bad. But consider this scenario. Let's make this a little, because this is just an excuse for me to segue into another topic actually. Consider this. The depreciation occurs as follows. So it's $1,000 new, right? So buying the stand new costs $1,000. It loses half the value by end of year one. At end of year three, resale value is expected to be $200. For instance, dropping all the way to 200. Okay, so it decreases rapidly in the first year, still probably a little bit rapidly in the second and third, but that's how it depreciates. Find D of T in this scenario. Still assuming linear depreciation in each period. Graph this function. For time equals 0 to 5. And assuming the value never goes below 200. So assume Jhevon takes care of the cart, but he'll always be able to get 200 for it indefinitely. So assume the value of the cart behaves that way. Loses half the value in the first year. Over the next 2 years, its value will drop linearly to 200, and it will pretty much stay at 200 for the remainder. What would such a function look like? How'd you do this one? He was about to do it again. I saw him. Did he actually do it? No, I think we're okay. He's like, Gotta keep an eye on it. What do you think? Or how would you start to figure it out? What do you think could be the first inkling?
Well, would you have to separate the fact that it depreciates 15% in 1 year?
Mm-hmm.
So would it be like 1 times half plus then the remainder 2 years?
1 times half? 1,000 times half?
Yeah, like 1,000 times half
Okay.
in year 1.
500?
Yeah, right, plus 100 per year after that. So it stops after 3 years, so you'd have to limit it somehow.
Yeah, so how would you do that? How would you write that down? Maybe first of all, let's draw a picture. How would that look like? What's gonna happen? This value over time. We know something happens in 1 year, something else is happening in the next 2 years, and then we have something going on. After 5 years is when we're gonna retire. Okay, so how do we describe the situation?
It's a steep drop to start off.
Okay? Well, what do you have?
So the value's 1,000, it goes down to 500.
It's 1,000, goes down to 500 by the first year. Goes all the way down here. Okay, now what happens?
Drops to 203, and by year 5 it's gonna stay
Okay,
as.
so we have 200, and that's at year 3. So it's still dropping, but slightly less steep, still like a line. So then that happens, and then it remains the same. These should all be straight lines. This has a little bit of bend in it. Those should all be straight lines. Now, how would you describe that? How would you describe such a function? Special kind of function here. And here's the segue. It is a piecewise function, we call it, which you're going to see from time to time. Sometimes functions do things differently depending on where in the domain you are, and you can represent things like that happening by a piecewise function. Depreciation in the real world would pretty much always be a piecewise function. Depreciates differently at different times. So it does one thing in one region. So there's one thing when your t is between 0 and 1. It's doing another thing when your t is between 1 and 3. And it's doing another thing when your t is between 3 and 5. These will overlap, so I can put equal signs on all of them, not worry about it too much. What happens in the first year? How would I describe the function in the first year? Which means I'm only focused on this part. Yeah, but how would I express it? So again, we have rise over run, it's a straight line. 500 over 1, so it means minus 500 is the slope. So what do I have here? So it's 1,000 minus 500. Should be able to find the equation of a straight line pretty quickly. Again, rise over run. So here, the drop is by what? The drop is by 300 over a 2-year period, right? So this is 300 over 2, that's 150 right here. 150 over 150t, that's negative, that's how much it's decreasing per year, and it had a starting value of what? What would you have here?
It'd be 500, right?
Would it?
I think so.
It'll be a little bit more than 500. It'll actually be 500 plus 150. Okay? It'll actually be 650. Do you see why? Or do you see why it wouldn't be 500? One, you have to realize that the equation of this, that's not the y-intercept of the line. Right? The line would extend, touch somewhere else here. Right? We need to figure that out. A couple ways you can do that. You can write it down like y equals mx plus b at first at one point and then just plug in a coordinate, 1, 500. Or you can realize that this takes effect when your t is 1, right? So at t equals 1, this is already minus 150.
Yeah, I get it.
But the value should be 500 at this
So
point.
you have to get to 500.
So you have to, you have to add that 500 back to the, you have to add that 150 back to the 500, right? Otherwise you could have done something like this. You could have realized that d is equal to minus 150t plus b, where b is the y-intercept. But then you plug in the point. You would plug in the point 1, 500. So the output is 500. T is 1. So you end up with your b is equal to 650. So you get that your d is going to be 650 minus 150 t. What about here? Between years 3 and 5, what is the equation of that line? What's the equation of that line between 3 and 5? Huh?
Just 200.
It's just 200. It's constant 200. It'll stay at the value 200. It's a horizontal line. So d here is a piecewise function. Because not all the time would your function behave the same way in all situations. Sometimes function changes depending on the situation. So such functions change their definitions depending on the region. Piecewise functions show up pretty often in this course, so I just want you to have seen one and how you might deal with one. If someone were to ask the question, what would be the value after 6 months down the road? What would you say? How would you compute that?
You said it's indefinite.
No, from the beginning, So year 0, I buy the stamp. Someone says, what do you think it'll be worth 6 months from now? How do you figure that out?
Find out what 1 month would equal out of the 500 depreciation. So 500.
No, we have this function. We've gone through the painstaking process of computing that. And someone says 6 months down the road, what are we looking at?
750.
How would you get that?
Since T is a 1 year, you have that, so half of that times 500
Right. So you have to remember that a function, and we'll talk about this a little bit later, a function will only output one value per input. So once someone gives you an input, you have to figure out which one of the definitions apply to that input. Now if someone says 6 months, 6 months is half a year. So when you look at these intervals, where would t equals 1/2 fall? It would fall into the first interval. And so you'd apply the first definition. So it's simply plug in t equals 1/2 here, you'll get 250, 1,000 minus 250 is 750. Okay? If someone says, after 4 years, how much is it gonna be worth? Well, you know you'd be looking here, so the value would be 200. So depending on where you are, depending on the time interval, how you compute something will change, right? And there are functions that have to account for that, right? Sometimes situations change. Sometimes the function isn't always the same thing. Sometimes when the situation changes, the definition has to change. You have to actually do something. So piecewise functions do that, which we are going to talk about functions in, I think, 1.4, and we'll repeat that a little bit. But I just wanted to introduce it to you now so that we can actually, I can actually show you something on your calculator. So I already showed you how to graph functions on calculators. Now I want to show you how to graph a piecewise function on calculators. I don't know why I have to pull it down twice. It's the same. So you can get out your calculators. So you can try this. One is to turn the calculator on. What were we doing last time? Okay. So I showed you how to graph. A quick reminder, you go to the Y window and you enter the formulas. So you can press the diamond button, press F1, you'll go to the Y window, you can enter the formula that you want to graph, and then you press the green button again and you press graph and it will graph it. And we also saw that you can change the window where it is, stretch or shrink, by pressing the green button and then going to window and setting the limits. Okay. So we saw all that. All right. Now let's suppose we wanted to graph a piecewise function. Let's say I wanted to graph the same depreciation function that we had earlier. So it doesn't. Probably let's make the numbers a little bit smaller. So maybe cut it down by a factor of 100. So we'll think of the highest point as 10, then it drops to 5, and then it levels off at 2. Let's kind of do that scenario, so you can probably see the picture nicer. Okay, so you would go to green, the Y window again. Let's just erase this guy. So here's how you'd enter a piecewise function. You're literally going to tell it where it works. So let's write this down. So it was 10 minus 5t, let's say. And that was between t goes from 0 to 1. Then we had what? Maybe 6.5 minus. What was the thing here? 1.5t, and that was t between 1 and 3, and then let's say it levels off at 2, and it stays at 2 between 3 and 5. We're going to graph that function. So you have to tell it not only the definition, but you have to tell it where you want it to draw that certain definition. And here's how you're going to do it. So the first function is going to be 10 minus 5 put x. Now, this part is very important. It's in the handout, but let's just go over it very carefully. You're going to put the such that symbol, which is just going to be a bar, and the bar you'll find right here beside the 7. I'm going to put that, right? So it's not just 10 minus 5x, it's 10 minus 5x with some given condition. And the condition is I want the t to be greater than 0 but less than 1. And you would literally enter that in. So you say something like, okay, I want the x value. Now to get the greater than sign, they're here. Notice that they're in yellow, so you'd have to access them by a second function. Okay. Now, and also, you won't see the greater than or equal to sign, so let me show you how to get those in. If you want to get the greater than or equal to, you'd actually press the diamond button first. So let's put x greater than or equal to 0. I'm going to press the diamond button and this guy. See, that's the greater than or equal to symbol. 0. Now you're going to put an and, right? So there are two conditions. So basically, if I want to say t is between 0 and 1, I have to say t is greater than 0 and at the same time t is less than 1. So we need to put a space, type out the word and. To get space, you're going to put alpha, and then the space word here. So press alpha, space, that gives you a space. And now we're going to, there's an and function that you can access from your catalog, but I think it's easier for me to just type it. So I literally just press the alpha key and type out A, N, and T. So that's what I'm going to do here. So alpha, A, alpha, and alpha. Then another space. Now I'm going to enter the second requirement, which x needs to be less than or equal to 1. So go to the diamond button, less than or equal to 1. Enter. Now that is how you would enter that thing. Right? So it's going to apply this definition, but it will only apply it under those conditions. When your x is greater than or equal to 0, and at the same time it's less than or equal to 1, so it only applies between those two. Then I can go to the next one and enter the second part. 6.5 minus 1.5x such that x is greater than or equal to 1 and x is less than or equal to 3. It's going to be that one. Then y equals 3. Now this one is kind of tricky, so be careful here. You see, if you just enter 2, it's going to give you 2 everywhere. Because even if you tell it a restriction with x, the calculator is not going to notice any x's here, and so it's going to be like, okay, so x is nowhere to be found, I don't care, let's just make everything 2. To avoid doing that, maybe I can show you. Should I show you that? Let's say I just enter 2 such that, and here I can enter x is greater than or equal to 3. Space. X is less than or equal to 5. So now let's say I want to graph this. So all I have to do now is go to the graphing window, green button graph, so the window is set weird. Okay, let's change the window here. Window, I believe we set this to be something weird last time. That's fine. X max, let's move that to 5. Y min is fine. That, let's move it to, say, 11. Now, okay. So now we should see. There, that's the first one. There's the second one. You see, now you see it gives you that 2, it goes all the way across. Is because even though you tell it that, oh, keep your x's between 3 and 5, it saw no x's in the first definition. So whenever you see that, what's the problem is, go here. The trick is to actually put an x in there, but to not give it any effect by just multiplying it by 0. So that's the trick. So whenever you're graphing functions and your lines are all over the place and they're not in the little neat holes where you want them, maybe you have an x that's kind of rogue, because if the calculator doesn't see that there's an x there, it's not going to restrict anything, it's just going to use the function too. Yeah. Yeah, you don't want that.
Yeah, why do you, exactly.
Yeah, I just said, if you do that, that's going to happen. So to prevent it from going everywhere, you have to add a 0x. Right? So you have to tell it some value. And now if you put it, say, x is greater than or equal to 3, and x less than or equal to 5, now when you graph it, 1, first step. 2, the second guy. 3. So now you see it doesn't go all the way across. It'll just keep it between 3 and 5. Because now it realized, oh, there's an x actually here. I'm actually plugging in numbers only for these values. Right? So if you only put a constant function, it's always going to do everything. So you get around that by doing a little trick. Type a constant plus 0x. Right, so that it actually computes the x values for a specific range. And so that's how you graph that piecewise function. And we'll take a break here, I guess. The next section we're going to talk about is going to be probably strange for some of you if you've never done statistics. But it's also going to use a lot of calculators, so the third calculator